First of all, let me give you a short overview over our products. So we are a vendor of agile production systems. So when I entered today the garage, I saw many cars that have at least one part which is assembled with one of our machines. So you get these production systems turnkey ready from us with NC programs, with automation, with the machines, and it's running in a very highly automated way. So normally you just switch it on, and then it produces over 450,000 parts per year. The main parts are cylinder blocks and heads. Here in this example, you have 32 single spindle machines. You put in the raw part here, you get the ready part from that station, and normally we have parallel production. So the part moves along through the entire production system like this. And here we have machines that do parallel processing. So it's decided at runtime which machine will do the next part. So these are very complex machines. Earlier we started with transfer machines. Now everybody uses production centers, and you can combine them by our SPECT family. It is a very broad range of different systems. We have a building block. In the simplest machine is a 4-axis machine with a disk magazine. We also have O-chain magazines. We have 2 spindle machines, like this one here, and so on and so on. And what you see here is only the top of the iceberg. So in totally, we have more than 10 by 30 different variants which we can configure out of the system. Why is it so much? So our customers are from the automotive industries, and in the quote we give them, there is one very important sentence, most at the end of the quotation, to say, okay, we built the machine according to your customer specifications. And whoever had contact with automotive industry knows that the customer specification is not a specification for the company nor for the plant. It's depending on the person you talk to. So you have sometimes 2 production systems next to each other, but have totally different specifications. And that's not a matter of time, it's a matter of the person you talk to. So, and we are coming from such customers, and that's why we said in our old organization, every person was dedicated to the order design. Because we said, okay, doesn't make sense to have a standard because everything changes every time. So most of our employees were attached to one of these departments. We had a small department of research and development, but only focused on mechanical topics. And so did our process. You can see it here, and you can see the process in a way where the technologies entered the machine tools. So we're coming from a mechanical development, the old transaxle systems. Then we introduced hardware and fluids development. And within CNC, we integrated software development. So, and at this time being, the mechanical development is the strong partner of the entire development. So they are starting with the concepts, and when they're finished, or nearly finished, they say, okay, I think we need those components, please, hardware, software, connect the cables. We give everything into purchase, so whenever something is purchased, you wait for the delivery, but you cannot change it in a very simple way anymore. And then at the end, so the software starts its work. And the software here is optimistically ending at the start of the assembly. Well, normally it's somewhere around here, and sometimes it's there. So, and this is the reputation of the guys. So if you want to be a well-liked person, yeah, you're a mechanical engineer. So, and if you like to be hated, you be a software developer. So this was the starting point, where we said, okay, this is for the future not a good solution. So, and even worse, we had a look at the data management. So every department had its own data management. So for the mechanics, we use NX. We do still do today, and we have a PLM database. And in this PLM database, we have project after project. You see project 1, project 2, project C, every with its single bill of material. In the hardware and fluids, we introduced ePlan recently, but we had no data management. So it was just project by project on a file server. And whenever we started a new project, we had a look at the file server and said, oh, this looks like, maybe this is the one that comes next to it. So I make a copy and create a new project out of it. And so did the software. We have 2 controls, either Siemens or Fanuc. So depending on the control, we have a file server where project by project is laid down. And so you decide, okay, looks like this is a good match. So I start with this project as a template. And every discipline chose for himself which was a good starting point. So we had lots of repetitive tasks to harmonize the data at the start of the project. And we had individual per project solutions, and we had tremendous quality issues. And we had no efficient way to fix errors for the entire product, because what we did, we fixed the issues of the project. And in the next project, depending on the time where we copied it, the errors were already there. So the, let's say, level of invention was very low compared to the level of management, of, well, discussion, what is the right base, what to do next, where are the errors. And this was the time where we said, okay, we want to use EEC, just the tool EEC. And we had 3 main goals to say, okay, I want to reduce the delivery time for our customer projects, because we detected that our competitors are quicker in the meantime. We want to improve the quality of our design plans, and we want to increase the standardization of the spec product. So this was it, nothing more. And at that time being, we said, okay, it's very easy. So we install EEC, we put everything in there, and then we are finished. Okay. And what was our general approach? We said, okay, we create a mechatronic database for all variants, and we use a functional approach instead of a component-based approach. Like in the speech before, if you're using EEC, you are, let's say, motivated to be on a more functional base than you're doing. And we said, okay, we need a clear interface for all the functions in order to combine them freely. And finally, to use the EEC to generate project-specific plans and structures. And this is what we did. So we took old plans, created components out of it, so small pieces which you can combine. We have a configuration HMI, and then we get the plans for the next project. So this is the general approach. And as easy as the approach is, the difficult is the realization of it. And that's why we said, okay, let's do it in 2 phases. Phase 1, the home base of EEC and ePlan. Let's start with hardware and fluids. And in the second phase, come to software and mechanics. At phase 1, we still thought it's just a pure tool introduction project, because it's hardware and fluids. And we have no need to change our overall business processes. because we're still talking only about the tool. We said, okay, in principle, it's very easy. We grab the project of the last 3 years. That's quite easy to find. Then to define a common function structure, not so easy, but working if you're not talking to too many people. Then next step, we modularize our E-plan structure. Okay, that's techniques. And then we migrate everything to EEC. So far, so good. And so our mind changed during that phase of the project very quickly, because at start, we were afraid of the amount of projects. We said, okay, we did so many projects in the last 3 years. Who would be able to monitor all of them to see, take the right solution out of them? But during the project, we struggled hard to agree on a standard. So because we spoke to many people and they said, hey, here, this is my solution. And the next one said, my solution is this. So, and nobody was willing to say, okay, that's a compromise I can live with. So in that phase, we said, okay, it's not about the tool. And even it's not about the process. It's about, are people willing to take a solution that they did not invent by themselves? And this is what at the end of the phase 1, we detected that people are unwilling to accept solutions other than their own. So, and this was the main target to attack. So because we had many complaints of people, we gave them our plans, our generated plans, and they said, well, no, I can't work with it. We say, why not? Yeah, I would have made it differently. Said, okay, but why? So well, I did it in the past this way. And this was the time being where we said, okay, we need a ticketing system, because in the first project, someone said, okay, do it this way. And we said, okay, if you want it, we do it this way. The next project, next employee said, no, I just want to do it the other way around. And so we said, okay, we need a ticketing system where you put into your comments, your bug reports, your, let's say, whatever you think. And then we have a common process on how our common base should evolve. So and with that, the complaints of the employees are vanishing, because they are part of the process. What is to be said? We are not only generating one standard out of the EEC, we are making it customer specific. So within our EEC database, you can have the same function here and here in different variants and different notations. So we are not, so I know many companies who say, okay, I have a standard and then I have a department that changes for the customer. We try to generate, at least for our main customers, out of the standard. So now coming to phase 2. EEC was introduced for hardware and fluids, and we didn't talk about it anymore. So people were used to use it. And now the question was how to integrate the software part and the mechanics part. So in the meantime, we had introduced Subversion to manage our software solutions. We had functional descriptions within Subversion integrated, the PLC and the ANSI software. In the PLM database, we have a product structure, we have CAD models, and we have the drawings. And the big question was, so how to proceed with software mechanics? And which business architecture to use? So how should the solution look like? And how can we motivate people to of different professions to cooperate closely? So you see from the, let's say, way of thinking, hardware and fluids, okay, they are next to each other. So, and they are quite near to mechanics, but software developers are different. And at that time being, so before we started the phase 2, yeah, our project changed dramatically. So from a tool introduction system project, it changed to a major change project, and with a focus on people, organization, and business processes. Yeah? So, and we reacted on it. So the first thing was we said, okay, the old way to do everything in the order design and to have only mechanical research and development, this cannot work anymore. We need a research and development, a standardization team that is mechatronic. Yeah? So this was the way the controls department came into life. And also we said what we want is we want a new process. Yeah? Get away from the sequential way, from mechanics to the assembly, into a mechatronic process. To say what we wanted is to say, let's configure a basic machine from the EEC, and then have a mechatronic concept team that looks on what to change for the project. And with that, get every department with a clear order to say what to do in this project. So, and it's not that somebody can say, I'm finished. So all departments are finished if the last department has finished. So because what happens in the old process? So here the mechanical designer has finished its work and he is in the next project. So he is not willing and he does not have the time to do changes. So this is why, so everything reported from assembly turns to be a software problem. So it's not that the software caused the problem, it's that the software has to solve the problem. Why? Because they are still working in the project and it's much more cheaper to change software than to change hardware. So, but the result is not the best solution. It's just the solution that was obvious. So this is why we said, okay, let's do it this way to work really in a simultaneous engineering process. And then when everything is finished, let's start with the assembly. And for the business proposal, by this, we reduce the time to delivery. Now, let's go a little bit more into detail about the business architecture. So because we had to decide how to integrate this architecture. And we had a look on two alternatives. Alternative one was to say, let's get rid of all the databases and migrate everything into EEC. So I have one large database, EEC, which produces the results, which will be then later on finished with the user tools. Or alternative 2, to say, okay, we want the EEC to be the central configuration platform for all of our engineering disciplines, but let it see as a logical way. So we still have our databases, we still have our tools, and in the middle we have EEC, who is doing all the variant configuration for every discipline. So we decided to use EEC as the configuration platform, so finally we decided for alternative 2. This meant to us to create interfaces to the used tools. By this way, we avoided revolution. So we let developers use their well-known tools. So they're still working with NX, with Subversion, with Step 7. And we keep our flexibility. We do not have strong dependencies between the departments. We have only just a logical integration layer. And the result looks like this. Here we have the EEC, which configures the machine. We later see on in a small film. And from that we create our E-plan plans. just as the standard does. And we create one configuration file. This one configuration file goes into a self-developed tool, we call it bomb generator, which has a CAD model, a PM module, and a PLC and a software module, which generates all the drawings and the models, etc., where later on the project works with. So the question is, why just one configuration file? In order to force people to work together. So I go back to this, because this is not out of the heads of the people. And if we would have given them the opportunity to configure mechanics separately, software separately, we would have configured the machine 4 times, and we would have gotten 4 times different results. So this is something we didn't want to. So we said, okay, in order to support this process, to force people to have one variant configuration over all the disciplines, we said, okay, there's just one point in time and one configuration file which controls all the different disciplines. So that works quite well. And we still had the question is, what is the contents of the configuration file? And our first approach was to say, okay, we export all the information from EEC. For example, the location of the parts in an assembly. And we started to store everything in very large spreadsheets. But this meant to us that we had to store the information twice in different locations. And we had one single point of truth, which results in resource conflicts. So the user feedback was, this is too complex to handle efficiently. This motivated us to say, okay, let's think about it, and maybe we find a smoother way. And we did. So we said, okay, within the EEC, I export only the configuration information. I said, okay, I have parameters and values. And what EEC does know is which parameter depends on each other parameter, which values are valid combinations, which are invalid combinations. So, and at the end, after a configuration process in EEC, we get an XML-based file with the current configuration. So we extract all other information from the sources at runtime. We have no redundant data anymore. And the con is we need consistency checking, but it works across all disciplines. So everybody's happy now. Now I would like to show you a small film. And this is what we call the 300% machine. You can see we have 2 chillers, a side chiller and a roof chiller. You see here we have a tool lift and a O-chain, which are at the same place. So this is a machine we cannot build as it is. But every possible variant is within that model. And if you have a look here at the motor, these are 2 motors that are at the same position. What we're doing now is to configure with the EEC. First, we choose the machine, and then, because it's very important for us, the second parameter is the customer, because it controls the specifications. Then you can choose the axis configuration, whether you have a ball bearing or a linear drive, etc., etc. At the moment, we have approximately 150 parameters, which control the variant configuration of the entire machine tool. And they depend on each other. So if you choose here another value, then you have to choose a new spindle. So now after we have finished the configuration, we have just one button. Now the button is to press, so start the configuration. And now everything is running in the background. So what you see here is something our usual employee does not get to see. So this is a server running. It takes at the moment approximately 3 hours to get the entire machine. Most of the time is the check-in and check-out of the drawings. So if we could get rid of this, we could do it in less than 1 hour. But anyway, it runs in the background. No one is attached with it. So there is no need that we make it faster. So where's my mouse? So let's go a little bit ahead in time, because that's quite boring. So at the end, I think you know best. We got the the plans from EEC, which we can then have a look at in ePlan. We have the compiled here PLC code, which is a ready archive to be transported into the machine. So we create also a bill of material for this project, for this machine. So, and what you see here is the special CAD model for this project. You see the, whoops, sorry. You see the O chain here has vanished. We only have the roof chiller, the side chiller has gone. And now when the here we have only one motor anymore. One side effect of doing this was that we started to model all the cabling in the CAD model. And these have been very interesting discussions between the production and the mechanical design, because from time to time we got to see that the cabling in the machine has a very different layout than we thought it would be. So, and that was the reason why we finally got to know why nearly every cable was too long or too short. Okay, so let me please come to a short summary. What we did in phase 2 was to migrate from a mechanic-driven or mechanically dominated development process to a mechatronic process, to a true mechatronic process where people cooperate and they are willing to cooperate, and where they like to cooperate because they see their benefits. And so our small EEC tool introduction project became in reality to a major change project. So we chosen EEC to be the central platform for the configuration of the entire product, and we are happy with this decision. So we configure hardware plans, fluid plans, mechanics, bill of materials, CAD models, drawings, and some Excel helper lists. We create the software. We develop the entire toolchain because the bomb generator is something we wrote or implemented by ourselves. And we can measure our first results. We have a very much better understanding of each other issues. So let's say, as I said in the beginning, so we have the light guys from the mechanics and the software guys. So this has totally vanished. And we see quality improvements of the design results. We have a much higher level of standardization for the spec product. And we have a reduced time to delivery. And what is very interesting, so when we created our first project, where we had the plans and the bill of material generated, we got feedback from the order design. They said, oh, wrong cabling. We said, okay, why? So here it's a cable in the plan, here is a cable in the BOM. Your cable's in the plan. I always ordered other cables. So, not possible anymore. So, well, it's still some change to do in the people's mind, but we are on the right way. Thank you very much.